My name is Seyyed Hosseini, and I work as a senior scientist at the Bureau of Economic Geology. I've been working on CCS for about 15 years and a few years also on hydrogen, but today I'm here with my CCS hat, basically, talking a little bit about potential of storing CO2. And being in Texas, I thought maybe put a few slides on CCS potential in Gulf of Mexico, Louisiana, Texas, which is going to be a major part of hydrogen economy. Sort of, we are talking about all these numbers that is going to be hydrogen generation, and looking at the hydrogen and CCS, what kind of volumes you are talking, can we do that? Have we done this kind of volumes of injections of CO2, before, or something equivalent? I put a few slides together. The first one and the next few slides are from, Clean Air Task Force. They have a good database as far as the projects that they're going to do CCS in the Gulf of Mexico. In the U.S., I zoomed in to the Gulf of Mexico, specifically Texas and Louisiana. So you see there is a few of them, and there is the bubble size is the volumes, quite a few million tons of CO2 going to be injected. This is just by hydrogen industry. One or two, I guess, are operational, and the rest of them basically are planned. The next I just put on top of that is the other CO2 that is going to come from other industry. So one thing that you would notice that when you put these maps together, there is a couple of things. There's going to be a lot of it, right? And some of them are actually concentrated in some specific areas, like Houston. I guess a previous panel mentioned, is a hot spot, so you will see that there is a bunch of them there. And technically and typically, a lot of these companies don't like to build long pipelines too, so that means the competition for injecting CO2 is going to be also focused on the specific areas. This is another, one of the discussions was that some of this CO2 goes for EOR, but at least these projects that are planned, if you look at it, again, this is the distribution based on the different colors. For some of them is used for EOR, and most of them are going for saline aquifer. I would say about maybe 80% going for saline aquifer storage. So a lot of volumes. So can we do that? And how much CO2 we are talking about? I took a few numbers from the U.S. roadmap for the hydrogen economy, and I did some numbers. So you can see that in 2020, that was the numbers. We are about 11 million metric tons of hydrogen production in the U.S. That 77% of that is coming from SMR. And again, another statistic to remember is 45% of total that we do is in Texas and Louisiana, okay? So I took the numbers. They have a projection that how much CO2 is how much hydrogen we're going to produce by 2050. And I took the average number and did some numbers. I think the average at 2050 is we produce about 42 million metric ton of hydrogen. And that would, if you wanted to do same amount of the SMR that we are doing right now, and assuming again 45% in Texas and Louisiana, that would mean that we will have about 1.5 to 2 gigatons of CO2 coming out of hydrogen production that we need a storage for. And
a gigaton is 1 billion tons.
Yes.
so between 1.5 and 2 billion tons, right?
2 gigatons of CO2 if you want the hydrogen to be clean. So again, can we do it? So at the Bureau, we have done some analysis on the storage capacity. This is a couple of maps looking at the storage capacity in the Gulf of Mexico, a couple of strips going all the way from Brownsville all the way to Louisiana. And this is a static capacity, and at the time we looked at it, I think this is the 2017 study that we looked at it, there is about 120 gigaton of storage capacity. And if you look at just the offshore part, it's about, 20 gigaton. One thing to remember is that in this study, we did not consider that the projects are going to be interacting with each other. So we just did an update that I don't have it to show here, but actually this number reduced by 1 order of magnitude when you're putting all these projects on top of each other. So that whole Gulf Coast in this formation, the whole thing is about 12 gigaton. So still we have good number of capacity, so compared to 2 gigaton. And we are just focused that study in one specific zone, geological zone, we call it Miocene, so there is multiple other zones that we can use. So it's sort of a good news and bad news that there is going to be competition. It seems we have capacity even when the competition comes in. There's going to be challenges. And my last slide is that have we done anything like that before? These are just studies, right? There's been discussions that these are just studies. Nobody has actually done this kind of thing. Just one example that I wanted to put is that the amount of the water that we have injected in the same area pretty much, Gulf of Mexico, over the past 30 years. These are real numbers. We have injected about 20 billion barrels of water in the same area, past 30 years. If you change the volumes, that's about 2.5 gigaton of CO2 actually. So we have done similar volumes, in orders of gigatons past 30 years. Potentially, we have the volumes to do it. Is it going to be easy? Probably not, because there is going to be a lot of CO2, and the 2 gigaton that I just mentioned, it was just from the hydrogen economy. There is a lot of other industries that they're going to produce CO2. There's going to be competition for space, a lot of pressure to put in there. But
they're straight up just CO2 capture industries. I mean,
yes.
Yeah.
Yes.
Yeah, you're right. Yeah.
So that was my few slides just to get things going. We can have more discussions.
Mojdeh Delshad is going to continue on the can we actually do this? What are the sort of...
No promises.
No promises. Here we go.
Does this work?
Yes, I think that's the...
Yeah. While she's setting that up, a little bit of clarification. I've been talking to people that they compare CO2 storage as a CCS. Currently it's called permanent storage. So when you inject CO2 in a saline aquifer, they think analog is hydrogen. Wrong. It's not an analog. CO2 is a liability. CO2 is a waste product. You're trying to get rid of it. So you're going to store it, unless you want to use it for CO2 EOR, and then also you leave some of it behind. So you produce oil. Hydrogen is the commodity. Hydrogen you inject, produce. And it's just basically whenever you have excess power, electricity, you want to just store it. When you need electricity, maybe seasonal, maybe yearly. And in my opinion, it also is going to give energy security to a country. The same way that we are storing nitrogen, natural gas, the way we have strategic reserves for oil. So when there is a shortage, you ship them out or you just use it for the country. So you always have to keep that in mind, that you're also going to increase the energy security. So again, we have to be careful these days. When you're doing the hydrogen production from fossil fuel-based material, and then you do storage of the carbon you capture, that is going to be called clean hydrogen in the terminology of Department of Energy. It used to be blue and then CCS, and now it's called clean hydrogen. And then if you are going to do CO2 as a hybrid storage and producing oil, that is going to be CCUS, so you're utilizing the CO2. So this is a schematic of subsurface. I hope the geologists in the group here, they don't criticize me for this picture because it may not be very realistic. But the point is, you have a lot of options in subsurface reservoirs. You can have, for example, oil reservoir, which is normally depleted. You do primary production, you do secondary, inject water, and then you have very little oil left behind that you have to do maybe enhanced recovery with CO2, and that's part of the also CO2 storage. So that's called CCUS. You can also inject CO2 in the depleted gas reservoir. So when you have a lot of methane, natural gas, and that can be just a CCS, so a permanent storage. So you don't produce anything, you're just storing CO2. Or you can also produce some of the methane that you have in that reservoir. So actually, I'm working on a project right now that's looking at possibility of injecting CO2 and producing the remaining methane from the reservoir. So you get some extra cash. And then if you go deeper in formations, and sometimes actually they're not that deep, is the saline water. And these are not drinking water. These are the water that you cannot drink. A lot of salt in it. So then you're going to store it, and now Department of Energy calls that permanent storage of CO2. And of course, there might be others. These are conventional reservoirs. And there was a call from Department of Energy that now they're interested to looking at the CO2 storage and utilization in shale. So that might be another set of subsurface that we can look into. So talking about some of the projects, just last month, Chevron, Talos, and Equinor, they announced the Bio-Bend CCS project in Houston. It's going to be a huge project, and they've already acquiring a lot of leases for pore space, and the numbers are really huge, and it's going to be one of the largest projects on CCS. And then as Seyyed was talking about the history behind CCS and both carbon and storage goes back to about 50 years ago. The first one actually was in 1971 in Texas. I'm going to show that one. But the problem is the scale of these projects. A lot of demonstration, a lot of small projects, a lot of CO2 EOR, but never like the scale that we're talking about today. So when you scale up a process, it's going to be a lot of challenges with it. Even from the oil and gas, when we do a CO2 EOR pilot, everything goes well, you produce a lot of oil, and then when you go to a larger scale, then you may not produce as much. So everything with the scale is going to create more challenges. So Petronova is another project of a CCS that was done again near Houston, about $1 billion project funded by Department of Energy, and then they were supposed to capture CO2 and then store it in an EOR field by Hilcorp. That project unfortunately didn't meet the criteria from DOE in terms of the capture capacity, and then it's been on hold for 3 or 4 years, and now a Japanese company invested in that project, and they're going to continue, and they're going to enhance their knowledge of CCS. So a lot of challenges with that project. Why they did not meet the capacity that they were supposed to capture. They had power outages during the project. They had CO2 pipeline shutdowns. They had bottlenecks at the facility. And then this is unpredictable, hurricane. So as I mentioned, if you read the literature on CCS, is considered as a proven and a really understood technology, but I don't think so it is for the scale that we're talking about today. A lot of projects going on, a lot of other previous speakers, they talk about that, but what are the persisting challenges for CCS? In my opinion, and what is going on right now, getting the permit. A lot of projects right now, applications are in the queue that they're not getting the permit yet because of they're not sure about the policies. Where do you want to get the very good pore space for storage? So that's where you need to have the geologist to help you to pick the best location and then maybe some of the petroleum engineers to tell you how to operate that. Pipelines, reduce project cost, improve efficiency for both capture and storage, safety and security of storage, site selection, most critical, injectivity. Some of the projects like Gorgon by Chevron in Australia, they were not very successful because they couldn't meet the injectivity. And you know what happened? They also had other issues of the impurities in CO2, and some of the water that they didn't dehydrate caused corrosion in the material. Caprock integrity, and a lot of others. So we really need to continue to understand, both in the lab, both geologists to characterize the subsurface, and then the modelers to be able to optimize the process. Innovation to improve the project economics. Do we have enough pore space for the future? As Seyyed mentioned, there might be some competition here. Do I have enough pore space for natural gas, for CO2, for hydrogen? Do I need to be concerned today? And construction equipment and labor costs has been increasing. So you have to factor that in your economics. Last slide. I participated with some of my colleagues in this fascinating experimental work that was done at the University of Bergen in Norway, that they tried to mimic the complexity of subsurface as a saline aquifer. So that has like a lot of different sands with different permeability, coarse with a high perm, fine with low perm. They included some faults, and a couple of these faults are actually leaky faults. And they injected CO2 here, and a lot of monitoring there. And so this is that big picture. They showed that at the Society of Petroleum Engineering last year. And there were a lot of groups that they were trying to model this experiment. And it was fascinating to see how far we are from our predictions with the models, even with the best models. More data that we received from the experimentalists, then we reduce that uncertainty. Even at the end, if you read that paper, you see how different modelers, the results are so different from the experimental work. So we're not done yet. We have to continue developing our models. We need to continue to do different types of experiments to be able to go to a larger scale. Thank you.
Awesome. Andrew Waxman is from the LBJ School of Public Affairs. You were going to tell us about some of the economic policy issues with hydrogen and CCS?
Yeah, I'm honored. I don't have any slides. Thank you. We can keep your lovely diagram, their figures up. They're great. The economists don't produce as nice graphs as engineers and geoscientists, so I didn't want to embarrass myself that way. It's a pleasure to be here as the sole social scientist on the panel. I think there are a lot of important policy, economic, even social justice issues at play with thinking about energy transition and particularly hydrogen economy. I'm just going to name a few things, and economists are famous for stating the obvious and then claiming that it's a brilliant insight. So I'll keep my remarks short. So one interesting point is that if we think about the technological options in the near future for hydrogen production, we've got conventional SMR production using natural gas without any CCUS. Obviously, that produces substantial greenhouse gas emissions in the atmosphere. We can combine that with carbon capture, utilization, and storage technology, in which case it becomes closer to a clean hydrogen production, as it's been discussed. And then we've got the electrolysis approach, which would use ideally renewable energy to produce electricity that's then used to produce hydrogen through electrolysis. As I'm sure has been discussed in previous panels, the latter option is, from a cost perspective, much higher. Obviously doing hydrogen production with CCUS is also more expensive, but less than electrolysis in general. One kind of point that's just sort of obvious is that hydrogen economy, in terms of thinking about the transport issues that were discussed in prior panels, involves one large set of infrastructure costs to think about how to transport and produce that hydrogen. When you add CCUS to the equation, you add a second set of infrastructure, which is basically how to capture, transport, and store that carbon dioxide. So that just makes the problem more complicated. It doesn't mean that it's impossible or not worth doing, it just makes it more complicated. Another sort of general thing to keep in mind is that when you think about the costs associated with carbon capture, which is the largest, by far, the capture component of CCUS is the largest component of costs because it's capital intensive, because you have to extract it at a compressed rate and a variety of other reasons. The costs per ton of CO2 removed scale in proportion to the purity of the CO2 stream that you're dealing with. So one relatively nice thing about hydrogen is that compared to, for example, natural gas power plants, the CO2 purity is greater. It's not as great as some other industrial processes like ethylene oxide and a few others won't get into, but it makes the cost of capture for hydrogen, especially through SMR, lower, which makes it an appealing approach, and it's why hydrogen production with CCUS is already something that's done at scale in the United States. But that said, I think it's important to keep that in mind, that the capture costs are important. Another aspect that was touched on by Seyyed and my co-panelist is when you're thinking about where to do hydrogen production with CCUS, the notion of hubs is super relevant for the reasons that were talked about in previous panels, that producing hydrogen in terms of think about its transport and use, producing it in areas that are located close to end-use locations is pretty important. A similar comment can be made about CCUS, which is to say that if one is going to invest the legal and economic infrastructure to put in pipelines and storage facilities, doing that in clusters is also really important. So hence the notion of having hydrogen and carbon hubs linked together. That said, there's a host of, as my co-panelists talked about, a host of economic and regulatory and political challenges that deploying this type of technology faces. One of them is that the permitting, as Mojdeh said, like the permitting for carbon capture wells is different than that from, say, conventional oil and gas wells, and it takes a lot longer to go through. There's a process that the state of Texas, state of Louisiana are sort of at various stages of going through to be able to issue those permits, what they call with primacy locally, rather than having to go through the U.S. Environmental Protection Agency's process. That could potentially speed up that process, but it means that moving this technology forward at a pace at which we would all like to see it move forward can be challenging. Also, pipelines are politically challenging things to get approved for a variety of reasons. So another industry for which carbon capture is more cost effective is fertilizer and direct ammonia production. And they're trying to do that in the Midwest. And putting in pipelines in places in Iowa proximate to those locations has proved to be a real political battle. And I don't mean to say that in a way that belittles the concerns of the communities who might be affected by those pipelines, but just to say that siting pipelines is a very challenging legal and political issue. One last regulatory point, and then I'll yield so that we can have more of a discussion, is the permitting itself is, from a legal perspective, quite challenging, which is to say offshore saline aquifer storage in federal waters is not something for which there is, at a commercial scale, a clear regulatory way forward at the moment. There's strong hope and there's lobbying going on to try and make that an easier process. Near-shore state waters are kind of, in terms of the balance of regulatory feasibility as well as being sufficiently far away from human activity and low-cost accessible, near-shore waters are a much kind of more appealing option, but then that starts to limit the set of pore space that becomes accessible as a result, as my colleagues are experts at talking to you about. And then, of course, obviously we can store onshore, but then the question is locating in locations that are from a liability, from a sort of being away from human activity perspective that are desirable locations can be challenging. So that's...
So, thank you guys. Thank you all so much. Andrew, I want to follow up just real quick on, do we have historical precedent for, did we have to deal with these same regulatory issues when we're talking about disposal wells, when we're talking about the sort of wells that you were talking about injecting on the coast? Was there regulatory ambiguity there too, or do we have I guess, a historical precedent for figuring these regulatory things out?
A lot of, I mean, in terms of, if you're talking about in terms of oil and gas sector, a lot of these things were dealt with at the state level and then figured out at the federal level afterwards, depending upon what we're talking about. I think the bigger issue is the scale of CO2 we're talking about storing underground is potentially quite significant compared to some of these other waste products, for example, right? And particularly if you're talking about the scale of demand increase that we're projecting. So I think that changes it substantially. I mean, the other thing is just storing CO2 as a waste product is a different issue than storing water underground or dealing with just oil and gas wells that have been taken out of action, for example.
And Mojdeh, that's exactly what you were talking about, right? The chemical makeup is,
Yes.
Yeah.
That's right.
And so the different challenges, are we so new in this space? I mean, we were talking about, CCS 50 years, talking about this for 50 years. Are we just so new in this space that we're still figuring stuff out? Or do we know these things, but we're trying to figure out a way to get around it?
Well, there were a lot of demonstration projects. Actually, Bureau of Economic Geology, they did a couple of those. Frio, Gulf of Mexico, and then Cranfield in Mississippi, very successful, small scale.
Sure.
I think the largest one was 1 million, Cranfield in Mississippi, but small scale.
Right.
And then what it makes it really challenging is like you have to monitor the CO2 for a long time.
You mean the EPA? You mean
Well,
state
yeah,
regulatory
so
bodies?
that's-
Everybody,
yeah.
right?
There's not a, I mean, this is the issue, is the regulatory framework for
That's
how
the
to
thing.
manage wells hasn't been well established,
Yep.
essentially. And so we're resting on essentially like, the litigation to solve this at the moment.
Right.
And so the question becomes, do state authorities step in and take over responsibility for these sites? Do the feds take responsibility for these sites?
Yeah.
There's not a clear legal basis. And so one of the issues is essentially, unlike other things, the CO2 has to stay there forever,
That's
basically,
right.
right? And so, this is somewhat analogous to how the federal government thinks about disposing of nuclear waste.
Sure.
And because that has to be stored, in secure locations indefinitely. And even that has proven to be a real regulatory challenge. There was a Yucca Mountain facility in Nevada, and then they didn't want it there in the end, and so it didn't happen. One other thing just to say is that, CCUS, unlike, for example, renewable energy, is a technology which only makes economic sense without a carbon tax if the federal government is paying for it, right? So we have this 45Q federal tax credit, which also includes now cash transfers as well,
right.
which varies depending upon the use and the storage location, but up to this point, the majority of large-scale CCUS projects in the United States have been used not to store underground in saline formations, as we saw earlier, but rather to produce oil and gas through enhanced oil recovery, right? And so we're transitioning towards, through the Inflation Reduction Act, toward doing more saline storage, but at the moment, essentially what had made this technology economical was being able to use it to produce oil and gas, right? And so in the absence of a carbon tax, which would create an incentive for people to reduce emissions, essentially, if we stop subsidizing this technology, it's not going to happen, right? And that makes the implications substantially different than, for example, hydrogen, which has an end-use value, right? If we make hydrogen production cheap enough, people will potentially use it, right? Whereas here we're just trying to figure out how to deal with the waste product.
Well, that's what I was going to ask you, too, is the way that we use this term CCUS, should we be saying, I mean, we had talked about CCS. The U feels like right now a very, very small part of this. We can commoditize and we can think about, you can think about crops, you can think about carbonated beverages, but that is such a drop in the, exactly.
Yes.
And so if you're talking about the S part of it, you need to be sort of focusing on exactly that, and that's what you're saying, is that there's going to be competition for that space.
Right. Again, what you mentioned, and I put some numbers, right? We are talking about gigatons.
Yeah.
And that's going to be, using the other usage really is not going to make a dent in the volumes that we are talking about. And in the context of, climate change and decarbonization and things like that. So you have to look at those numbers in that context. So you really need, and even, EOR, we have done these studies. Even EOR, if we assume we want to do full EOR in about 5, 10, 15 years, you would run out of the EOR options.
Yeah.
You know, you need to go to the saline if you really want to go to those volumes.
Yep.
And again, you need a lot of pore space. A lot of those pore space we have access to. Hopefully, in the Gulf of Mexico, it's a good geology that we can use. Again, the issue of doing larger scale projects, that's the one that is sort of standing at this point, you know, having more and more of those.
Yeah.
And I think, I guess we mentioned that the issues with the regulations, the EPA, that's why some of the states like Louisiana and Texas, they are considering to get the primacy. But even getting that from EPA has been a little bit difficult process. It seems Louisiana just had a drawback in getting the primacy. And I know that Texas is looking to do the same thing. And EPA is really behind of approving these things. So hopefully if you have these projects can do it and show, you know, that we can do these things. As of last week, they have 200 applications to look at these permits for larger scale CO2 injection. That's a lot of applications. And they have approved only 2. That was, I don't know,
So
10 years ago.
Is it capital? Is it that the feds just won't permit? What's the sort of is it risk? Is it all the? I mean, maybe it's all the above.
I think from EPA's mind, I'm not talking
Sure.
on behalf of EPA, but I think they are also concerned, and they think when they are going to put a stamp on something,
Sure.
you know, that is going to mean something, right?
Right.
So
This
they
works.
have done a few smaller scale, like Illinois project, Decatur project, but that one again was a few million ton of CO2. But now they want to give a permit for, let's say, Chevron, that is going to do 100 million ton of CO2.
Yeah.
And then there is another site next to it that is going to do that. So they have to be more, looking at the details a little bit more, and that's why they're just a little bit delayed. And I think a little bit overwhelmed, actually. They do not have the resources to evaluate these applications.
There was supposedly one person reviewing the permits up until very recently, and that was not that person's only designation, right? But I mean, I think also there's legitimate regulatory concerns,
Absolutely.
which is that there are frontline communities that live adjacent to a lot of the industrial facilities. They've had decades, in some cases centuries, of concerns about what was going on. Some of these in Louisiana, they were on locations that were formerly plantations, so there's communities that have real concerns about what the what decarbonization energy transition means and what the future of these locations are. And so I think there's, a political and regulatory process to try and think through how to address all of these intersecting issues.
We heard. Yeah, go
do you
ahead.
mind if I just
No,
make
not at
a comment here?
Please.
I had a project with EPA a long time ago. It was for groundwater contamination. And we were basically proposing a technology that we add some chemicals to expedite, the production of the organic material. And these are really poisonous stuff. So EPA, I think we made a report of about maybe 100 pages of telling them exactly how we're going to do it. And then they came back and they said, you need to tell us when you finish with this project, how much of that chemical that you inject is going to stay in the aquifer. So we had to do a lot of numerical simulations and uncertainty analysis, and then we just say, okay, we just end up with 25, and then they approve it. So you have to do a lot of paperwork and engineering and to be able to prove it to them that you be successful in this project.
Right.
Otherwise, they're not going to approve it.
Well, and like Andrew said too, I mean, there are legitimate regulatory concerns. There's a reason the EPA is there. They're worried about contamination, of course.
You have leakage problems.
But
you
at
have
the
to
same
prove
time,
it.
if none of this can get done, there is a problem. And some of it, like you said, is, and I've heard this 100 times too, it's staffing. A lot of it is.
Yeah, they don't have enough people. Yeah.
I think the timeline that the government has for these projects and
Yeah.
funding we talk about these billions of dollars that is going to these projects, right?
Yeah.
I guess hopefully somebody behind these agencies, they are saying, okay, we are putting this to the Department of Energy, we are funding these projects, now they are coming, and the next step is going to be EPA. So they should have put enough funding on EPA to have more people to also review these processes.
Yep.
And I think they are trying to catch up now.
Sure.
But they are behind, way behind.
One other topic just to touch on here is just, thinking about for things that, for processes that could use carbon capture utilization and storage technology, where hydrogen fits on that scale. So I mentioned cost earlier and sort of capture costs, but another thing to think about is essentially, what are the alternatives for decarbonization to what's being produced, right? So, I mean, hydrogen has a potentially appealing use for, for example, like blast furnace, alternatives to conventional blast furnace, or large-scale shipping or trucking, depending upon the particular context. There are, in some cases, alternatives, in some cases not. Other industrial processes, like cement production or, ethylene oxidants, they're not readily electrified production processes. So in some cases, CCUS may be the only option if we want to continue producing some of these things in the near term without producing CO2 emissions. Right. As compared to what a lot of the focus in the CCUS literature is, or policy discussion, which is about electricity production, right? Yeah, sure. And so there you're talking about, coal-fired or natural gas power plants being retrofitted, or new ones having CCUS. And there, there would be substitution with renewables potentially, right? And I think, there's a reason to think that all of these options should be on the table, but one thing to keep in mind is essentially what are our alternatives, and how is policy incentivizing us to go one way versus the other.
Well, that's the other thing, too, that I was thinking about a bunch, is the viability of some of these projects are going to depend on 45Q, and they're going to depend on CCS to make sure that those are actually viable. And so then you're sort of, you're cart before the horse, maybe. We heard, I wanted to touch on this, and I think this is a really interesting idea, and I may be just absolutely out of my mind here, but we heard from John Koss at Sempra Infrastructure, and he was talking about hydrogen and LNG, and I was thinking about, is there a scenario in which if you're producing hydrogen, but you're also producing natural gas, that you're fighting for space within your own company for that storage? Is that...
Well, actually, right now, European and also here in U.S., they're considering depleted gas reservoirs that you have a lot of, still some natural gas remaining, is going to be a good target. First of all, you already have existing infrastructure. The subsurface. It's not like saline aquifer that you really don't know what is down there. Right. And then you can inject hydrogen. Some of my papers actually about that, injecting hydrogen in a depleted gas reservoir. First of all, it's going to help you in terms of maybe you have enough pressure, so then you may not need as much cushion gas. Sure. We're learning about that as well. And then the impurity of the hydrogen. So you're going to get a mix of hydrogen and methane.
Yeah, exactly.
And so then depending on the end use, if they want just pure, like, the fuel cells, they want pure hydrogen, there may not be a good target. But then if it's a mixed for, heating homes and, maybe trucks, that is okay to have a little bit of natural gas. Sort of a blend, then it's okay. Yeah. But then the pipeline becomes an issue. Do you have the pipeline that is...
the molecule size, right.
Absolutely.
Yeah, exactly.
Yeah, but we're looking at that, yes.
Okay. Do we have time for a couple of questions? Yeah. Okay. Perfect. Yeah.
Any questions?
We answered them all. I think. One back there.
Thank you. As someone who's somewhat familiar with it and learning about the CCUS. I'm also interested in international relationships, and you mentioned Japan acquiring this particular power plant. Other countries, are they interested in injecting CO2 into U.S. territory? just interesting conversations with other countries.
I can take it.
Yeah, of course.
I mean, injecting CO2 in the U.S. or doing CCS in their own country? In their own, I mean, our team have been doing CCS for over 20 years. And I've been part of the team for about 15 years now. And the number of the projects, the map that I showed from Clean Air Task Force, you can zoom out and it shows you all the projects in the world, and you will see that there is quite a few of those. So we are doing active, actually, training for East Asia, for South America. Europeans actually, are not very behind the U.S. I mean, the number of projects is smaller, but some of the projects that they have done, like a Schleifner project, they have done it for 20 plus years, injecting CO2 in saline aquifer in the water. So they have quite a bit of strength. Project Northern Light in North Sea, they are building ships for transporting CO2. They have 2 finished. So it's a very active, community in CCS, not in the US, in Europe, in East Asia, in Middle East, and South America. So they are actively looking at it. But I guess US and Europe probably are ahead of the curve. Yeah.
Yeah.
Hey, what is the biggest techno-economic challenge for one, direct air capture, and 2, for point source?
What's the question?
What is the biggest techno-economic challenge for wide-scale implementation of CCS for direct air capture and secondary for point source?
Well, if you do the direct air capture, then there is no relation. This panel is about hydrogen, right? So there is no hydrogen. You only do the fossil fuel based power plants or some other natural gas facilities that you capture CO2, you generate hydrogen, and then you have to store the CO2.
Right.
Okay.
So it'll be the point capture.
Yes.
That's what we're dealing with here.
That's a point capture that has no connection with, and then right now it's too expensive. Department of Energy investing significantly on DAC. Also, there are projects in the Middle East, Abu Dhabi. ADNOC is doing that, but currently expensive.
Yeah, it's just cost basically right now, especially with DAC.
Very expensive, yeah.
So I just, as a non-engineer, I think part of the issue with DAC is the heat transfer issue, is being able to absorb CO2 at a low enough temperature, because otherwise you have to produce quite a lot of electricity to operate the DAC.
You're exactly right. It's the cost, but it's specifically the energy input. Yeah, that's exactly right.
Yeah, and I guess you mentioned the concentration of the stream that comes for the capture is an important part. In DAC, you are capturing CO2 from the air, that the CO2 concentration is about 420 ppm, which is really low. That means a lot of energy. That means expensive. Yeah. But DAC with solar, with wind, Department of Energy just announced $2 billion funding. One of them is going to be in Texas. GE, in collaboration with Oxy, is going to do it. Yes. We are having a small role in that project, actually. So that kind of money has to go from Department of Energy and basically get the incentive to do the research, to deploy it, and see how it goes. But challenging.
Well, one of the things is, so on point sources, there's the distinction between pre versus post-combustion capture. Yep. So if you can produce a pure oxygen or equivalent fuel source, use that for whatever your process is, and then produce a pure stream of CO2, the costs are significantly lower. That's a very social scientist description of either pre-combustion technology, or there's also oxyfuels and other alternative. If you're going to burn coal, for example, and then let the flue gas come out and then filter out particulate matter and other gases and then get the CO2, it's much more expensive, much more challenging to do cost effectively.
I'm moderating a panel in New York on DAC.
John, got a question?
2 weeks.
I have maybe it's a crazy question, but have people thought of just not requiring monitoring when you put CO2 in the ground? So, I mean, you're, trying to store the CO2 there. The worst that can happen, I suppose, is it all goes back in the atmosphere, but by the time that happens, you now have direct air capture technology and you save the world in a different way, and people figure out how to turn CO2 into plastic or something. I mean, how fast does it come out of the ground? I mean, what really is the risk of just not monitoring it, or will it really just come flooding back out into the atmosphere?
Well, I can say a little bit about that. It all depends on where you're going to store it, and you have the caprock integrity to seal the CO2 down there. So if you have good idea about the seal, you may not worry about it. And then making sure that you're not going to diffuse CO2 in the cap rock, or you cause fracture and make CO2 going up. So it all depends on, and every reservoir is different. There are reservoirs that very thick, cap rock. There are reservoirs that very thin cap rock, and the properties of those cap rocks are different. We did a project a while back that question was asked. What if you have CO2 that is going to leak from the saline aquifer that you stored it? So numerically, we showed that, okay, saline aquifer is deep in the formation, and there are cap rocks, shale that is going to have very low permeability. It disconnects different sands. Even if you cause a little bit of fracture or diffusion of CO2 in the first cap rock, it's never going to get to the surface. We numerically show that. But regardless of that, when we had the teachers from high school that we were doing a workshop for them, every one of them, they said, we're concerned. I said, what is your concern? Well, CO2 is going to leak. And I said, where is it going to leak? Well, to the air. You already have CO2 into the air. So why are you concerned? Well, it's going to go into my drinking water. I have a well outside, my farm, and what if the CO2?
It's called LaCroix.
So you have to be able to respond to all of this. That's why I'm saying education and training of the school kids and teachers going to be critical for both hydrogen and CCS.
Can I just add a quick comment?
Of course.
15 years ago, when we did the pilot projects, we asked everybody to bring any kind of monitoring tool that you have. Let's do it. Let's look at it. Yeah. But the idea has been that to minimize that and say, okay, that one didn't work, this one didn't work. And we are trying to get that message to EPA, to the regulatory agencies, that really some of those things doesn't make sense. It's not helping the CCS community if you really want to do the larger scale. And another comment is, really, for CO2, the concern is not small leakage. If it's something massive happens.
Yeah.
Okay? And we have looked at the numbers. I guess when the concentration of the CO2 gets beyond like 10% in a small space, then, maybe you get, pass out or get dizzy or things like that. So really concern is not like a small leak over, long periods of time, which EPA sometimes, asks for it, which is not probably reasonable. But those big things. And we have never had one of those. The biggest thing that we have seen, one of the pipelines in Mississippi that had an issue, and there has been one natural case that happened in Nigeria, one of the lakes, the CO2, and Lake Nios, you can look it up, that one, the volcano CO2, the volcanic CO2 sort of erupted. And that one had some fatality actually there. But that was, again, because large volumes of CO2 released suddenly, that's what happened.
And we don't do that level of monitoring for CO2 EOR.
Yeah.
I mean, one thing, as a social science, I didn't appreciate until I learned about this, is it's not as if someone's blowing a bubble into a giant, there's not like a balloon underground where it's going. It uses sort of the same thing that capillaries in your blood hold on to oxygen. It's the same thing so that you get little bubbles that bind all over. So you have to get them to all pool together, then go through a fissure and come out, which is, I'm told, hard to make happen.
It's hard to make that happen. We have tried to actually make it happen. It's difficult.
Yeah. And there are new technologies. Some of the professors in petroleum, they're working on it, that maybe you can add some chemicals that is going to increase the CO2 solubility in water, so that it's not going to be as mobile and buoyant. So there are people still working on new technologies.
I guess kind of the same line of questioning maybe, so CO2 leaks aren't a problem. Should we be worried about increased seismic activity when we're trying to push all this CO2 underground?
Yes, quite a bit of concern. That's right.
It could be a concern. I just actually finished a study last year for International Energy Agency Greenhouse Gas Emission Committee, and looking at the induced seismicity in CCS projects. So we looked at 36 projects that we just did a literature review, looked at all 36 projects that we can find over past couple decades. not just in the US, everywhere, to look at induced seismicity specifically. I'm not going to go through the details, but really none of them had a major earthquakes. The CCS, including CO2 EOR. So that was the good news. But again, I'm not going to say everything is rosy because, again, the issue is scale, right?
Yeah.
We have had 36 projects, 2 in Japan, 1 in Middle East, a couple in Europe, a few here and there. But when we go to the scale, it could be an issue, right? So I'm not going to say it cannot be an issue. It depends on geology, how much you're injecting, how you are doing the monitoring. But I can tell you, we had good amount of technology to prevent these kind of things. We have good amount of knowledge to do that. In the Gulf Coast, that I show a map, we have injected past 30 years along the Gulf Coast, Houston, drive from Austin to Houston, the same area. We have injected 20 billion barrel of water, the oil and gas industry and from other resources. That's a lot of water. And we have never had an issue from induced seismicity because the geology, I'm not going to go through the details, is very good. In Oklahoma, they did the same thing.
They had problems.
They had problems. They had induced seismicity because, they didn't, watch for a few things, but now they figured it out. They're now controlling it. So it may happen, but we know how to control it. You have to manage it. You have to plan for it.
Yeah, the site selection and operation.
Yeah.
Yeah, right.
Yeah, in California, it's a bigger concern.
Yeah.
Okay, well, thank you for an excellent panel. So before we go, I'd like to thank all the people involved. Krista, who did so much, John, Nora, NEI, the EI student team, Monique, Liz from CEM, everybody who's helped out. And of course, Brian put a meaningful amount of time into this himself, to tell you the truth. So appreciate it. Now we have the networking and poster session, so please join us for that.